Hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms and stuff related to it. Let me just adjust my chair. The date is 2025 April 2nd, and in my last video you may remember that I talked about the thing that I overlooked and how one of the things that I concluded was how to find the plateau or the plateau levels, how to find the plateau levels more accurately, so that while I calculate the dip sizes and dip size percentage, I can always factor in the plateau level and the peak levels. Yeah. So today I worked on this specific notebook file dedicated to finding the peak level and the plateau levels, so that I can find the dip sizes easier. So, the notebook I will be covering in this session is titled Genetic Algorithm Peak Plateau. Duh. And what I do here, as written here in comments, notebook to find ways of computing peaks and plateaus. So I import the ordinary stuff. However, this one's new. Import ast or import ast, and you'll see why I did that, as I've saved 7 all result list for top 10% as a txt file or a text file, and in this notebook I read those in and I used the ast.literal evaluation, so that it would just convert what it read directly into a Python list or Python list of lists. Well, more accurately, it's actually a Python list of lists. Yeah, I think that's the right way of saying it. So I read in all the 7 files using 7 files, each from the normal distribution, log normal, uniform, exponential, von Mises, Pareto, and variable, and I check. I just check their lengths for now. So, this is another way for me to check the dimensions. And they all check out. I'm not going to run anything on Google Colab, but yeah, here are the results when you run them. And then I make a list of max constraint percentages from 0.05 or 5%, and then 0.1 as in 10%, all the way to 100% or 1.0. And here are the initial plots for some initial plots. And this is when the this is for the available all results list top 10%, and when the maximum constraint percentage is at 0.05 or 5%, and these are all the 5 iterations. This is for probably this is the 11th, so that is probably 0.55, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, yeah, 0.55, so 55%. Yeah, so all the files have been read in. This is the 11th. I mean, this is when I is 11, which means that it's the 12th. So this is when the maximum constraint percentage is at 60%, and now we see peaks and we see the plateau, and therefore we see the dips as well. So all the files have been read in properly. We see the peaks again, yep, there, and then there we go. So my first idea of finding the peaks and plateaus was to calculate the gradients, as in you take one value and then you subtract the value before it and then divide that by 1, and that is the gradient. So in a list of 500 elements, you would have 499 gradients, and that's what this looks like. Well, not this, actually this is what it looks like, the gradients. But and if we plot it, it looks like this. Because this is the original plot of summed utility values, or the average of top 10% entities in terms of their summed utility values, and the black dash dotted line is the maximum, and then the red one is the average. So as you can see there, the black one is not exactly the plateau level, it's slightly above, as you know, by definition it's at max, so it's not there, it's technically not there. And the red line, red dash dotted line, is below the plateau level, as averaging all of this would mean that including this part as well. So yeah, it's obvious. And let me just use the paint shop again, and yeah, so back with this. So the red one is the average. Oh shit. The red line is the average of all of this, so therefore it's below the plateau. The black one is the maximum value of these, so it is going to be above the plateau level. So quite obviously, again, and quite self-explanatory, the plateau level is in between this black and red. So how do we find that? That is a question. So if we have a look at the gradients, as we can see here, I think this is better if I just put this down here, like there. So the gradients are the slopes. So obviously the gradient is really big when we go from 0 all the way to somewhere like here or here, which is why the gradient here is at above 600. And then the slope instantly decreases, which is why the next gradient goes all the way down here, and then here, and then here, and then here, and then the gradient stays almost the same here around this red line. As we can see that there are almost no changes here, so it's obvious that we don't get any changes here. So for this, you know, you might just think, why not just center everything around here, find the index, and then say that, oh, we found the plateau. Yeah, sounds easy, doesn't it? Yeah. When we have a look at the gold one, not this. Oh, we'll get back to this. This was the solution, but we'll get back to this. But when we actually have a peak and a plateau, oh shit, peak and a plateau and an actual dip happening, like for instance here, for instance, we do have a bit of a peak, and then we have a plateau. So it goes up like it does here, and then plateau. I mean a peak over here as well, maybe here. Yep. Let's see. Yeah, so about here is the peak, and then we have a plateau over there. So when we look at the gradients, it's not easy to say if this part is the plateau or this part is the plateau, because in terms of gradients, this is, you know, kind of similar. Of course, this bit is higher, so we can just deduct that this is where the peak happened because of the slightly higher level of gradients. Then again, what is slightly higher? What do I mean by slightly higher gradients when we have this? So in order to know what that phrase, slightly higher gradients, mean, we need to exclude this. We need to find a way, a logical way of doing that, which is kind of complicated, and things will get really quickly convoluted. So that's not a good way, right? And if you look at here, look, same story. Okay, maybe here it's easier because now we've had gradients all the way up at, you know, above 600. It quickly comes down and then slightly goes up, plummets down, comes back up, and then stays there around the red line. So we can say that, oh, maybe this is the plateau, because the gradient hasn't actually changed for quite a long time, for quite a number of generations, for maybe like 400 generations. So yeah, it's easy to say this is the plateau, and therefore from generation 130 to 150 to 500, we add that up and then average it, and voila, you have the plateau. But that's not really straightforward. What we're basically doing is would just be the same as looking at this graph, looking at this plot, and then just saying that, looking at that graph, and then saying that, oh look, we have this graph, we have the bulge, why not just say that plateau is here? There's no difference. So it's not such a good idea to do that. And same thing here. Oh yeah, another challenge here after that is based on what we've seen from yesterday and maybe 2 days ago, we don't really know for sure when the maximum percentage goes up. We don't really know for sure when this peak will happen. It can happen here after the huge climb, or slightly after the huge climb, as we've seen here, or in some rare cases, or in some kind of slightly rarer cases, it might happen here after generation 200. This is not something we've seen when we were dealing with a fixed set of constraints and fixed set of utility values. When we've had those items that I conjured up, and those utility values that I just made up, and those constraint values that I made up, which were coincidentally around the 70% maximum constraint percentage. But usually when that is the case, the peaks would happen somewhere here. But when the max constraint percentage is set to 14, so that's the 15th one, so about 70% or 75 or 80%, it will happen here after generation 200. And if you look at the gradients, sure, I mean, it sounds easy, right? But there will come a time when it's not so obvious. What if the peak never happened within 500 generations? Maybe it will happen in after generation 670, and we never saw it. Then, well, the plateau is still here, but the point still stands. Kind of. There's no way to be actually sure. So, one solution for now, I think the best one for now that I came up with, is getting the average of averages, as in getting the average of the moving averages. So, for example, I would get the moving averages of 50 elements, of 50 values in the list. And then, yeah, I did that. And then here's the histogram of that, which is, like this. And then I got the average of these moving averages, and then I plotted it, which is this one. See, sum of average lists and divided by length of average list, which is the average of averages in gold. So that is this line. So, and if we zoom in, that is this line. So, and you'll be able to see that it is kind of close to the plateau level. It is between the black and the red line. It's sometimes below the plateau level of below what we might conceive as the plateau level, sometimes above it, but overall I think it's a great way. Now I can always adjust the breadth of the or the width of the moving average. For example, now it's 50 elements, 50 values. It could be sized down to 40 values, or it could be a relative size, like 10% of the entire length of the list. But yeah, the point still stands. So that's what I did, which is what I got here in this example. When there were no apparent peaks, and then therefore no apparent dips, the yellow line still kind of closely, well, I think those are very redundant words, closely approximates. The yellow line is around the plateau level, kind of, when there are no apparent peaks or dips. And when there is a dip, for instance like this is what happens. Look at that. The yellow dashed dotted line is kind of below the actual plateau, or what we would actually say, consider to be a more accurate plateau level, but it's there, it's close, and I think this does a good job for now. Let's look at when we have a bigger, higher peak and more of a dip, more pronounced dip. Now we have a better plateau level. I think that's fair, right? It's still in between the black and the red line, and it has to be because the red line still includes this. The black line is the maximum. So our job was to find the right line between these two lines, and the yellow dotted, well, the gold dotted line does a good enough of a job, I think, and it will serve greatly as a plateau level. So this was the average of averages, moving averages. Yep. So, but I wanted to try for every maximum percentage and for every type of distributions used. So here we go. Right now at 5%, when we use the normal distribution for both the utility values and the constraint values, and when the max constraint percentage is at 5%, we don't see anything because all the lines are just stacked on top of each other. 10%, 15%, 20%, 25%, 30%, 35%, 40%, 45%, 50%. Now we're starting to see those two lines. 60%, 65%, 70%, 75%, 85%, 85, 90, 95, 100. So here, the blue lines in this case are the plateau levels, and if you look closely, the blue lines approximate the plateau level quite well. They are consistent. They're quite consistently all the time there, regardless of where the peaks are. And then when we start not getting peaks and plateaus, not much of them, because of the reason that I said last night or in my previous video, the reason being that if the maximum constraint percentage is high right now, the way I'm doing the evolution does not introduce new entities because the selector function doesn't eliminate the entities, because the maximum weight threshold is actually non-existent, and therefore there's little procreation, or rather no procreation, and everything just becomes stagnant and stale. But anyway, the blue line approximates the plateau level, maybe slightly below in this case, but still kind of there at 95. This was for the normal distribution. Log normal, 5%, 10%, 15%, 20%, 25, 30, 35, 40, 45, 50, 55. See, now we get the dips, kind of. And we see that the blue dash dotted line is kind of at the plateau level. It's hard to see, or rather it's hard to conceive all of this as as a plateau, because everything's kind of oscillating all the time. But at 60%, more understandable now. At 65%, oh yeah, now the blue line is the plateau level. 70%, yes, for sure. 75%, yes. 80%, oh yeah. Even though the peaks, only 2 peaks happened, the plateau level, we see that. And for the exponential distribution, same. You now start seeing the two lines begin to separate. Okay, at 45%, 50%, 55%, the blue line, 60% over there, 65. Yes, now blue line is the plateau level, 70 plateau level, 75 plateau level, even though the peaks happen at different generations. At 80%, even though one plateau, even though one peak, yeah, all these 5 peaks happened at different generations, about the same generations, different generations, and here, all at different generations, and one was happening, and then the whole evolution ended. Even given these conditions, the blue dash dotted line closely approximates, very much closely approximates the plateau level. And at 85%, again, no peaks happening, but we do have the plateau level. 90%, 95%, 100%. Yeah. For the von Mises distribution, same story. At 45%, we see them separate. 50%, yes. 55, yes. 60%, yeah. 65, oh yes. 70%, oh yeah. 75, yes. The blue is the plateau. Blue plateau. Blue is the new plateau. Plateau. Blue plateau. Plateau. Blue plateau. Blue plateau. Yeah. Sorry, I got distracted. 80%, 85%, 90%, 95, 100. So all of the blue dashed dotted lines are very close to the plateau level. And again, may I remind you, this is the average of the averages. Average of the moving averages. Pareto distribution, same story. Same. Now the blue line is starting to look like the plateau level. Very much so. Very much so. Very much so. Very much so. Yup. 90%, yes. 95, yes. 100, yeah. Slightly below the actual plateau level, but I think I'll take it. Variable distribution. Yep. You see that? Yep. Sometimes, again, slightly below the plateau level at lower maximum constraint percentage. But when the dips when the peaks and the dips do happen, the blue line closely approximates the plateau level, more closely. Yep, there we go. There we go. Very good in this case. There we go. Slightly above, or slightly or below. I'll take it. Yep. Great. What is this? Yeah. So that's how you compute the peak and the plateau given a list. And of course, by averaging those peaks and plateaus, I'll be able to get the overall peaks, overall average peak levels and the average plateau levels as well. And I can just apply them to the plots and safely, in a robust way, calculate the dips and the dip percentages. So going forward, I think this will be the method I'll be using. Average of averages and average of averages at most. So it's like average squared. Not actually squaring it, but average squared. You get what I mean. Okay, thanks for watching. Well, see you next time. Bye.